Okay, so this is the Chapter 19 notes for confidence intervals for proportions specifically. So back in Chapter 18, we had already talked about proportions with the whole idea of p hat, so coming from the sample, and then we even did a little tiny bit on x bar, so sample means. Now we're going to focus specifically on proportions alone, and that's what we're going to do for the rest of the unit. We'll get back to sample means next unit, so unit 6. So what we have here, so first thing we're going to talk about is confidence interval. So up here at the top, with this confidence interval, it's an estimate plus or minus the standard error. This is actually going to be on your formula sheet. So if you take a look at the top of, it's the second full page in the packet that I gave you, you're going to have estimate plus or minus margin of error, and then underneath that, we're going to have all of the different types. So there's going to be proportion, one proportion, two proportions, one sample mean, two sample means, all of that stuff. It's in that big table. So instead of them giving you a whole bunch of million different little tiny formulas for confidence interval, they just give you the gist of what it is. So we need to know what that means for us. So what we're going to be doing, or what we're going to be using, is that standard error that I talked to you guys about a little bit. Remember that we use standard error if we don't know the standard deviation. Remember, standard deviation is from the entire population at large. It's not normally realistic to expect us to get that, though. So we will then use the standard error in situations where we don't have the standard deviation. So the idea here is that we want to be able to figure out like a lower bound and an upper bound, so this whole idea of an interval. Lower bound and an upper bound, and say, we think that it's going to be between these two values that we're looking at. So, we still have this notion, though, that proportions is going to follow the normal model, assuming that the conditions are checked and met, and we need to make sure that that's okay. So if we have our normal model here, and we do remember that the mu sub p hat is just going to be p, and the sigma sub p hat is going to be the pq over n square rooted. So if we were to go ahead and label this model just like we did before, we would still have that whole p in the middle and then going up and down standard deviations. So we would still have the p here in the middle, and then we would go up a standard deviation. I don't want us to get locked into the whole sigma or s here, so I'm just going to write it out in words. Or 2 standard deviations, so on and so forth. So we're going to be able to go label this just like we normally would. And remember that this is going to be the sampling distribution of the p hat. So this whole thing, these are going to be our p hats. These are the things that we're concerned about. And we usually talk about 1 if we're talking about a test. So here's this idea that I was telling you about. If we don't know the standard deviation, then we're going to use this whole standard error thing right here. Notice the only difference between standard deviation and standard error. With standard deviation, you actually know P and Q from the population. In this case, standard error, we have to use P hat and Q hat, which actually comes from the sample. Okay, so here we go with our confidence interval for P. Now what's really nice is everything that we did in the last chapter, 18, we can still do here. I am just adding a little tiny bit to it to be able to find an interval. So not just a probability, we're actually trying to find an interval. So lower bound and upper bound. Still going to check the conditions, those haven't changed. But now we have this new thing. So this is our number 2 bullet here. We want to calculate the 1 proportion z interval. We actually have shorthand for that, and that is the 1 prop z int. And saying that on a test, that you're going to calculate or compute, or that you can do the 1 prop z int, is totally acceptable. So what that looks like, well, using the formula, remember that it is the statistic, so our p hat, the thing we care about, plus or minus this margin of error. All right, so then we've got different versions of this. So the p-hat is the actual statistic that we care about. Plus or minus, well, this is how we find the margin of error. So, and this is going to be pretty important. We want to make sure that we keep this straight. To find this whole margin of error, that is the critical value times the standard deviation of the statistic. The critical value is going to be dependent on the type of model you get to use. Since we're talking about proportions, and proportions, because we're talking about the normal model, those are z's. You know that from first semester. So our critical value is going to be a z star. The z star we can either find in the back of our book in a table, it's actually in your formula sheets also, or we can use our calculator, and I'm going to show you guys how to do that also. And then the standard deviation of the statistic. Well, if we don't know it, we're going to have to use the standard error. So keep in mind all the things I'm highlighting right now in yellow represent the margin of error. So if I jump down here, now I've got my critical value, which again is dependent on the model that you're using. We're going to use z's because it's normal, and the standard error of the statistic. So again, down here, more highlighting, this whole z star times the square root of p hat q hat over n, that whole thing is your margin of error. So you need to keep that in mind. Then at the end, because we always interpret in context, I am whatever percent confident that the true proportion of blah, 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 whatever the context is between that bottom bound percent and that that top bound percent. Okay, so now we're on to the values of our z star. So we can flip to the back of our book. It's page A120 in the very, very, very back. And I'll talk to you guys about this on your formula sheets too when I get back next week. Or we can go through and just let our calculator do it for us. So if we want to find the confidence level in decimal form, we're going to use this little formula right here to help us find it. So this whole z star is equal to the inverse norm of 1 minus c divided by 2. So now be careful when you type this in because you might actually have to have an extra set of parentheses just in case. So communicate effectively with your calculator is basically what I'm saying. So to be able to do the 80% confidence, I am going to go to my distribution button where my normal CDF, my normal PDF, all that business is, and I am going to go to my inverse norm. So I'm just going to write here what I'm typing in. My inverse norm, it opens a set of parentheses in my calculator. I don't know if it does it for you guys or not. What we're going to do is we want to do 1 minus the confidence level in a decimal. So for 80%, it's going to... That whole thing needs to be divided by 2. So for me, I have to make sure, just because I have an older calculator, that I put extra sets of parentheses around things. So you might want to make sure that you do the same, because it's not 0.8 divided by 2, it's 1 minus 0.8, all divided by 2. So if I were to type this into my calculator, I would end up getting 1.2815. So if you want to pause for a second, see if you can type in the rest of them, same format, and then unpause this, and then we can check and see if you and I got the same answers. Okay, so here's what I got. Now, I realize that when you type this into your calculator, you probably got a negative number. Remember, though, based off of what the formula is used for, this helps us with the margin of error. If we take a look back up the page and we take a look at the formula, it is plus or minus my z star. So it doesn't matter if you're dealing with the positive or the negative aspect of the z star, because it gets both of them in the formula. I tend to just write down the positive one. Not that it matters though, but remember when you plug it in, it is going to be plus or minus, so both of them will be accounted for. One of the things to keep in mind here is that we are talking about an interval itself, so this whole beginning and end. So these z stars give us those two cutoffs, so again, plus or minus. You can actually put plus or minus in front of these. I would like you to take a look, though, that the more confident you become, so from 80% confident to 90% confident to 95% confident, so the higher your confidence level goes, notice that your z-star is getting bigger also. So what that means, so if we were to take a look at this 99% confidence, if I were to take a look at what this normal model looks like, just in general, and I want to talk about this whole 95% confident, well, if here's my 0 in the middle, because these are standardized values because of the z's, this is at plus or minus 2.5 approximately. So that means that I'm at 1, 2, almost over 2.5 here. Over 2.5. So this area here is my confidence area. Notice how large it is. So the more confident I am, the larger my area is going to be. So the larger I have to throw my net is basically what I think. So I want to be 99% confident that I am going to catch a lot of fish. So the net that I use to catch those fish is going to be huge. If I'm only going to be 80% confident on catching those fish, then my net that I'm going to use is smaller. Hopefully that makes sense. Okay, so here we have our first example. And just like the examples that we've done in the past, we're kind of just doing little steps before we get to the whole full-blown confidence interval. So here we've got this problem where the guy says the margin of error is plus or minus 4%. Explain what that means. Okay, so remember 4% is, with margin of error, it's kind of your wiggle room, like how confident do you think you're going to be type of thing. So with this, I would say that the TV newsman believes that the true proportion of whatever we're talking about here is within 4% of his estimate with some degree of confidence. So if he is 90% confident, then he says that the true proportion is within about 4% of my estimate. That's what that wiggle room means. So that whole plus or minus 4% is kind of like a buffer zone. So if we get this written down. So it's got that wiggle room. All right. Okay, so moving on, now we're at the bottom of the third page of your notes. So we've got this computer printout that it's basically telling us something about the fraction of cars that are made in Japan. So they told us that it's z interval for proportion, so that means that they did a 1 prop z int. That's what that is saying. Then they're telling us how confident they were. That's what the 90% confidence is right there. And then the next thing they're telling us is the actual interval. So we've got our lower bound and our upper bound. For us, we're normally going to see this written as, well, an interval notation. Kind of like you guys did domain and range a million years ago in another math class. We would actually write these in parentheses. So we just need to explain what this means. So I would say, based on this sample, because it's specifically about this, so based on this sample, we are, whoever we are in this case, so whoever did this study, they are 90% confident that the true proportion, so we're thinking about our final statement here when we do intervals, that the true proportion of, the context is Japanese cars, or cars made in Japan, cars made in Japan, is between, and then we take these two little guys at the bottom and we write them in percents. So is between 29.93% and 46.98%. So here I've got my explanation. So they are 90% confident, so 90% confident that the true proportion of cars made in Japan, so that's my context, is between, and there's my lower bound and my upper bound of the percents that they told me. Okay, so here we go. Full-blown confidence interval. So we want to estimate the unemployment rate in the United States. Suppose a SRS, remember SRS is a simple random sample. That's nice. We like that. That helps with the conditions. Of 1,000 Americans showed 83 are unemployed, create and interpret a 95% confidence interval to estimate the true proportion of Americans that are unemployed. So the first thing that I like to do, and you guys know this, is I like to identify the stuff that I already have. So I know that my sample size, or my N, is going to be, or at least they told me, is 1,000. I also know that my P hat, because it's information about the sample itself, they said that it's going to be 83 out of that 1,000. So I know then that my decimal here is going to be 0.083. You'll notice that they didn't tell me anything about the actual population of Americans with unemployment. So I don't have P in this case, which means the best I can do is use P hat. Because I don't have P, because I don't know anything about the actual population at large, I cannot use standard deviation either. I can use standard error though. So keep that in mind when we do our calculations. So first things first, after I identify what I have, are my conditions. So the first one I like to tackle is the random or at least unbiased. I normally just attack them in order. So what was really nice about this was they said it was an SRS, which means I have a simple random sample. So SRS of Americans. That satisfies the random or at very least unbiased. So we're good there. Hand it to us on a silver platter. All right, the next one is going to be the 10% condition. So my sample isn't too big. Well, if I have 1,000, I'm pretty confident, actually very confident, that that's less than 10% of all Americans. Okay. Then we've got our next one, which is our sample, which is our large enough condition. So we have to do our NP and NQ. So go ahead and fill that in. Remember, we want it to be at least 10 successes and at least 10 failures. And I should realize almost immediately, as soon as I put some thought into it, that this is definitely going to be satisfied, because in the very beginning they told me that there were 83 out of them. So there's my successes, and if there's 1,000 total, then that means there's got to be 917 failures at least. So we have at least 10. So that's good. All right. Large enough is satisfied. All right, now we've got our conditions satisfied. We can go ahead and move on. So now what's kind of nice is I am not going to say that I'm going to use a normal model. I am going to say that I'm going to do that one prop z int business. Once I say that, I can now actually, once we get to this point, I can go straight to my calculator, plug everything in, and then just plop down an answer. Or, and that counts as mechanics as long as you say the name or give the formula. I'm going to go through it the first time though, because we want to be able to identify what the formula looks like, not just the, oh, I have this one prop z int. Who knows what it looks like? I can't identify it in a multiple choice question. That we have to be able to do. So, or they may show you some steps on the free response and you have to continue the rest of the steps. You need to know what you're actually looking at. So, I know, since my conditions are met, I can use, and I am going to say, the one prop z int. All right, so here's what this thing looks like. Remember, using our formulas, it is p hat, or the value we care about, plus or minus our critical value. The critical value comes from the different type of model that we're going to be using. So we are going to use a z star since this is going to be the normal model. times the standard deviation if I had it, but I don't. So I am going to use the standard error instead. Okay, so I know that this is my p hat, so just establishing my formula here for us, plus or minus my z star. Remember that my standard error is p hat q hat over n. So now, let's start plugging stuff in. Oh, we need a z star first. So my z star, remember I can use the table in the back of my book, or I can use my formula sheets, or I can actually use my calculator. So since I want to be, I think this says 95% confident, so I'm going to do my inverse norm of, so for me, 1 minus 0.95 divided by 2. Or I can just look back a couple pages in my notes, because I already did this one. So my p hat, value I care about, 0.083. Plus or minus z star, for me, for this, is 1.9599. And then take out my p hat q hat over n. So I've got 0.083 times 0.917 all over my sample size, which is 1,000. So at this point, all I do is I grab my calculator. So I'm going to type in the minus part first because I want the lower part. So I do the 0.083 minus 1.9599, type that guy in, and I end up with 0.0659. Then I type in my upper. So I basically just use the exact same entry from before, and instead of it being minus the z star, I do plus the z star, and that gives me 0.1000. I think there's a 9 after that, or a 5. So now I just write my conclusion in context. So I am, and then fill it in. So now with my statement written down, take a look at this. This is all of the work that I need to be able to do to use the one prop z int. Now, like I said, I will show you again after we get to the page with the calculator stuff on it, how we can get rid of the showing as much work as we are. We can go straight to just the answer, which is still technically the mechanics as long as you say one prop z int. So I've got my conditions checked. I can use so since my conditions are met, I can use my one prop z int. I have my work for my one prop z int. Please keep in mind though, that this whole z star equals inverse norm, that is not something that I would normally write down. The only reason why I have it written down is because I'm not there with you guys right now. So, and then go straight to my interval. Notice that I write it as interval notation, just like this whole idea of domain and range from before. And then I've got my contextual statement down at the bottom. So now we're at the bottom of page 4. I want you guys to go through and do this 90% confidence interval. So you don't have to check the conditions. However, you must say that the conditions were already satisfied. So please keep that in mind. You can't just jump straight into finding an interval. You have to say the conditions were satisfied. So I can use and then say what you want to use. So I'm going to pause this, go ahead and fill it all in. And I recommend you pause, try to get it all filled in, and then check and see if we match. Okay, let's see how you did. So since the conditions are met, I can use my one prop z int. I wrote down my formula again. It's just like anything else. The more you get used to, the more you write something down, the faster you're going to pick it up. So I always write down the formula in the beginning till I get used to it again. And then plugged in everything. Notice that my z star is the only thing that changed because my confidence changed. So make sure that you did the whole inverse norm 1 minus 0.9 all divided by 2, or flip back a couple of pages in your notes. So the setup is identical. The p hat and the q hat and the n haven't changed. We're still talking about the same type of information. But the one major change that we do have is that our z star changed, so be careful. And then I'm 90% confident the true proportion of Americans that are unemployed is between, and those are my two values. Now, if you sit back and you take a look at the previous problem that was 95% confident, and this problem, the 90% confidence, you should be able to look at the size of the interval to see how the confidence, like your level of confidence, actually affected what that thing looked like. Okay, so how confidence and sample size affect a confidence interval. So if we want to decrease our confidence level, then we're going to go with a smaller interval. So decrease our confidence level, smaller interval. That means that our Z star is smaller. If the Z star is smaller, then that means we're going to have a smaller margin of error. Likewise, flip side, with increasing a confidence level. Okay, now if we increase the sample size, so that means that the denominator for our margin of error is going to get bigger. If the denominator of the margin of error is going to get bigger, then that means the entire value of that whole fraction is actually going to get smaller. So we have a smaller margin of error. When we have a smaller margin of error, that means that we have a smaller interval. Likewise, with decreasing a sample size, the denominator of a fraction is going to get smaller, which means the entire fraction itself is going to get larger. So we have a larger margin of error, larger interval. Okay, so now we get into the calculator skills. This is kind of awesome. It's just like everything else, we have to go through the hard work of dealing with the formulas before we get to the little golden prize at the end with the calculator. So we're going to go to, we've gone to the stat button a lot. We haven't done it in a little while though. So first semester we did a lot of stat calc. So now we're going to do stat. And once you hit the stat button, there's a third option on the top that says test. So I want you to scroll over until you get to test. It just opens up a whole bunch of different things. And we're actually going to use a lot of those this semester. But we want to scroll down until we find one prop Z int. And we want it to say all three of those, or excuse me, all four of those things. One prop Z int. We make sure that we select the correct thing. Then once we've done that, it gives us these options. So X is the number of successes in the sample. So remember that P hat is the proportion. So it's not the whole proportion we're looking for. We don't want a decimal here. We want the actual number of successes themselves. So this is just going to be the numerator of the P hat fraction. So X, then we've got N, which is our sample size, and then our C level, or C. It's going to be our confidence level. Make sure that you type it in as a decimal, and then hit calculate. So now here's the beautiful thing. If we take a look at this very bottom part on this screen, it is okay to use your calculator on any exam, including the AP, if you name the interval or write down the formula. This wonderful thing here are your mechanics. It's pretty nice. Okay, so here we go. President Obama approval rating from, wow, 2 years ago now. 48% is based on a sample of, so they're telling us N. Margin of error of 3%. Okay, so they're telling us about the formula for the interval, but not the whole interval. This is what I mean by we need to know what the formula looks like and how to manipulate it. So what confidence level was used? All right, well, the first thing I'm going to do is I'm going to identify what I have. So his approval stands at 48%. So that means that my P hat is 0.48. Which means then automatically that my Q hat is going to be 0.52. They also told me the sample size, so that's my N. I believe that it was 1,500 people. And then they gave me the margin of error. So margin of error is going to be plus or minus. And at 3%, that's 0.03. All right, so what I'm going to do is I'm going to take out my formula here. So I know that for my entire interval, it's going to be, and I'll go off to the side here since I don't need the entire interval, but I do want to be able to look at the formula, is going to be P hat plus or minus, we are talking about proportions, so Z star and then P hat, Q hat, all over N. All right, so here I've got my formula. Remember that where the Z star is, that whole plus or minus business, that is going to be the margin of error. So this whole thing right here, that's the margin of error. All right, so if the margin of error is actually equal to that mess, let's write that down because that's the part of the formula that I care about. So the margin of error is going to be equal to plus or minus Z star and my P hat, Q hat over N. Okay. Well, they gave me almost all of these things, so I'm just going to plug everything in where it goes. Okay, so the margin of error is plus or minus 0.03. The right-hand side is plus or minus, so I don't really need the plus or minus because it actually includes both sides. So I can cancel those guys out. So I'm just going to do 0.03 equal. So I dropped the plus or minus on the left. I'm going to drop the plus or minus on the right. All right, so Z star. Oh, that's what I'm trying to find out because they're asking me about the confidence level. That's the Z star information. So if I can find Z star, then I can find the confidence. All right, so Z star here. Then I plug in everything else I know. So I know the P hat and the Q hat. So P hat was 0.48, Q hat's 0.52, all over N, my sample size, 1500. So I'm going to go ahead and solve this. So I'm going to do all of the stuff in the square root, and then I'm just going to divide that to the other side. So my Z star, if I type this in, is going to give me 2.3256. Now, remember, this is plus or minus, actually. So I go back to what I had talked about when we did Z stars originally. So at the very beginning of these notes. So there's my 0. All right, so I've got 1, 2, 3, 2, 3. Not the best looking picture, but we get the idea. Okay, so we want to go past 2 here. So there's my positive Z star. And then past 2 here, there's my negative Z star. Remember that the confidence is between those two things because it is an interval, low bound, upper bound. All right, so think about what we've done before and how we find something like this. So I think we've got 2 Z cutoffs and we want to be between the two. I'm thinking normal CDF on this. So I'm going to do my normal CDF with my lower bound being the negative Z star and my upper bound being the positive Z star. I'm going to type that into my calculator, and it looks like I got 0.9799, which I am going to say is probably a 98% confidence. So I think this is 98% confidence level. Notice that we have stuff coming back from first semester with this whole idea of Z's, still a normal model, so we use normal CDF, or we've used inverse norm before, so we are kind of pulling up stuff from first semester. All right, so same idea, we want to do the exact same process, but this time I think we're looking for the sample size, so we're looking for N this time. Okay, so I'm going to pause it here and I'm going to fill this all in. So my recommendation to you is to do the same. Pause it, see if you can answer this question. So now we're talking about the unemployment problem. So don't use the Obama's approval rating on the previous page. That's what I did the first time that I did this. Make sure that you flip back far enough to the unemployment problem. So we're still going to use the same P hat from the unemployment problem. I'm going to use the same Q hat from the unemployment problem. And we've got our margin of errors, plus or minus 1%, our confidence level, so they're telling us the Z star. Now we have to find N. So plug it in, see what we get. Okay, so I went through and identified by underlining and then marking next to it what it was in the question. Brought out my margin of error formula, and then because of the different algebra that we have to do on this one, I went through, it's not necessary for you to, I went through and showed all of my steps to try to get the n by itself. So if you had a hard time with the algebra part of it, these are the actual steps that I went through to solve it. And then I ended up with a decimal for n, so 2923 point something. But remember, we're talking about people. So we can't have a decimal of a person. That doesn't make any sense. So whenever we're talking about n, and for that matter, whenever we're talking about x, for thinking about typing something into our calculator, for the one prop z in, they have to be whole numbers. They cannot be decimals. They cannot be fractions. So keep that in mind about what they actually represent. And then I have my statement down at the bottom. Okay, so interpreting confidence level, I'm going to spend a lot more time with this with you guys. So why are we 95% confident? Well, 95% of all possible samples will result in the one prop z int that contains the true proportion. So it is not that basic of a concept. And like I said, this is going to be something that we spend more time talking about. And then here we've got our last one. So we're going to create a 90% confidence interval for the percentage of all auto accidents that involve teenage drivers. I'm going to explain what your interval means. Explaining what your interval means is the final statement when we do an interval. So I am 95% confident that the true proportion of blah, 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 blah. So that's B. C is going to be explaining the 95% confidence level. So that's what the previous one was. And then D, we're going to use our interval to help us answer the question. So I'm going to go ahead and pause now and do A and B. So this is just running an entire interval, doing the calculation yourself. Okay, so A and B. So I went through with my conditions. The randomly selected auto accident, so that's good. 582, sadly, is less than 10% of all auto accidents. And then I have to do my NP and NQ. And I haven't flipped back at the previous slides yet, but I'm guessing I forgot to put the hats on that P and Q. Remember, if we don't know what P or Q is, we have to use the hats here. So for my large enough sample, I ended up with 91 is definitely bigger than 10, and so is 491. So large enough is satisfied. Since the conditions are met, I can use one prop C int. Okay, so I showed all of my mechanics. I just let the calculator do everything for me, though. So I went back to the calculator page that you guys have in your notes, followed exactly what I had written there. So I typed in what my X was, which was 91. My N is 582. My confidence is 0.95, or my C level. And then I hit calculate, and it did everything for me. So if you did it with the formula, you should have gotten pretty close to the exact same numbers that I have. And then B is actually explaining my confidence interval. So I'm 95% confident the true proportion of auto accidents that involve teenage drivers is between, and it's my bottom bound and my top bound. Okay, so for C, we're explaining the confidence level. This is different. So what it means is, if we take all possible samples, possible random samples, and we go through and we calculate a one prop Z int on every single one of them, then 95% of those confidence intervals should contain the true proportion. So about 95% of all random samples will produce confidence intervals that contain the true proportion of this population.